All right, thank you for the invitation to speak. I love this this online seminar, and I hope that it will continue even once we eradicate the COVID virus. Let's say, fingers crossed.
You mean our community, our Poisson community eradicates the COVID virus?
Yes, I don't know. We will play our part, I guess.
Yeah.
Okay, so I'm going to speak about branes and in symplectic groupoids, and I will explain what is a brane, but I will not explain what is a symplectic groupoid. And this is several projects. This talk represents several projects in preparation with Francis Bischoff and Joshua Lackman. Joshua is my current PhD student, and Francis graduated last year. Okay, so what is a brane? What is a brane? So branes exist for any generalized complex structure, but I'm going to explain the case of the symplectic structure. That's the most important case. So if you have a symplectic manifold, M, omega, what is a brane? Well, the brane will be a coisotropic submanifold, which just means that the Poisson structure takes the conormal into the tangent. We all know what is a coisotropic anyway. Okay, now, but the coisotropic is equipped with an extra piece of data, which is a Hermitian line bundle, U, and this line bundle has a unitary connection. That connection, the purpose of it for now is that it provides us a two-form, the curvature, which is a real two-form, real closed two-form. Okay, and this curvature must satisfy two conditions. The first is that, well, I've drawn it here. So if you have this coisotropic, any coisotropic will have a characteristic foliation. And I've drawn it as if this characteristic foliation has a leaf space. I've drawn the leaf space as the coisotropic mod equivalence relation. Okay, and we all know that the symplectic form, when restricted to C, will descend to the leaf space. That's symplectic reduction. And so in other words, omega obviously will descend to the leaf space, but we are requiring that not only does omega descend, but also this curvature for this unitary connection also descends. So both omega and F descend. And when you descend them, you can invert omega. Omega is a symplectic form on the leaf space, so we can invert it. We can combine it with F, and this will determine an endomorphism of the tangent bundle of the leaf space, right? Because F takes you from T to T star, and then omega inverse takes you from T star to T. So we have an endomorphism, and the requirement is that it must square to -1. It seems very strange, but that's the definition. So as a result of this, we have a complex structure on the leaf space coming out of nowhere. There is no complex structure on M or on C, but rather there's the kind of miraculous appearance of a complex structure on the leaf space. And because this complex structure is built from omega and F, it turns out that F and omega together, if I put them together like this, F plus I omega, this defines a holomorphic symplectic form on the leaf space. So this is a very strong condition, because in order for a complex manifold to be holomorphic symplectic, its dimension must be even. But that's a complex dimension. So that means that the real dimension of the leaf space must be 4K. Okay, so it's a very strong condition, and we cannot expect such branes to exist in great numbers. Okay, but if the dimension of the symplectic manifold is 4 or higher, it is possible for these to exist. Okay, so if all that you learn in this talk is this definition, I would be very happy. So please ask any question if you want at this point.
Hi, Marco. So
Louder.
The integrability of the complex structure is automatic from...
It's automatic, coming from the fact that both F and omega are closed.
I see. Is this a particular kind of brane, or this is the most general?
This is the most general brane.
Okay, thank you.
For the A model. I'll get to that in a moment.
What about non-degeneracy? Does it say something about F or about the line?
F is not non-degenerate. F can be degenerate. Of course, it must be degenerate. It has to descend.
No, but I mean the descent, right? This in the end, you want to get a holomorphic symplectic structure.
Yes.
So this symplectic structure must be non-degenerate.
Yes, yes. This square, the omega inverse F squares to -1. So this is a non-degenerate endomorphism.
Okay.
Yeah, it's definitely non-degenerate.
This is Ezra. I have a comment on your remark, Marco. You said
Yes.
this is the most general kind of brane, but it seems to me that branes should form a differential graded category.
Yes,
and
Ezra, we're getting to that.
graded
Yes.
0, so not the most general.
In the classical A model, when you're looking for supersymmetric boundary conditions, this is the most general condition on a submanifold.
Oh, on a submanifold.
Yeah.
Yeah. Okay. Good.
We're getting to that.
Okay.
Patience.
Marco,
Yeah.
Matthias here.
Yes.
I'm a bit confused about the quotient of C being a manifold. This
It doesn't matter.
not to happen
So
in general.
I'm not assuming that it's a manifold. I've written it here in terms of the quotient of the tangent space. It's a pointwise condition.
I see, but then can you make this argument of the holomorphic symplectic structure on the quotient locally?
Yes, correct.
Okay.
Okay, moving on. So I think you all got the point. You're asking all the right questions. So, okay, so let's look at where this condition comes from. How did I come up with this bizarre condition? It wasn't me who came up with it. It was Kapustin and Orlov. But I'm going to give a different way of obtaining this condition, a simpler way. So consider the symplectic form and view it as a generalized complex structure. It maps T plus T star to itself, and it squares to -1. It is a complex structure on this extended tangent bundle. Now, whenever we have a submanifold C and a unitary line bundle on C, right, we can produce from this a version of a tangent to the submanifold. This consists of all vectors which are tangent to C and all one forms. These one forms are not necessarily one forms on C, but they're one forms on the ambient space, such that when you pull them back to C, they agree with the image of the vector field under the curvature of the unitary line bundle. So the point is, what I'm trying to say is that specifying a submanifold together with a unitary bundle immediately defines a natural maximal isotropic subbundle inside T plus T star. And this maximal isotropic subbundle is defined along C. Okay, this is called the generalized tangent of the submanifold. But of course, it depends on what the value of the curvature is. Now, if the curvature was 0, if it were a flat connection, then the pullback of this one form to C would be 0, and therefore this would be in the conormal bundle. And then I would have tangent of C plus the conormal of C, which is obviously a maximal isotropic. They cancel out. Okay, but the same holds true for any value of the curvature. So we get a maximal isotropic. And the definition is simply that we call this a brane in the generalized complex structure if the generalized complex structure stabilizes this maximal isotropic subspace. So it's very similar to the condition of being a complex submanifold, namely that the tangent of the submanifold should be stable under J. Okay, and if you write out this condition, then you will get these conditions that I wrote before. So it's in that sense, it's a very simple condition. It's just saying that it's a complex submanifold. Another way of thinking of it is that this thing is this was made very clear by Maxim Zabzin in his lecture notes on the subject, that J represents a supersymmetry. And this represents the Lagrangian boundary condition given on that submanifold. And this condition is simply saying that it should be a supersymmetric boundary condition. It just makes it very crystal clear how you get these conditions. And you can see very clearly that the conormal is automatically contained. If C restricts, if C is in the conormal, then it restricts to C to be 0. And therefore, if I take X to be 0, that will be contained inside this generalized tangent. And if I apply J to this conormal, it's just omega inverse applied to it. And so this condition obviously tells you that omega inverse sends the conormal into the tangent. So it obviously means that it will be coisotropic. The second condition is more difficult to see, but it comes essentially from the fact that, yeah, j squares to -1. Okay, so that's where it comes from. It's a brane in the sense of generalized complex geometry, and actually there are plenty of branes in generalized complex manifolds in general. They don't necessarily have to be symplectic, but this is the case of a symplectic manifold. Okay, so let me give some examples of these branes. Okay, so the best example, the one that everyone loves, is the case where C is Lagrangian. So if C is Lagrangian, then that means that the characteristic foliation is the whole Lagrangian, which means that the quotient space is just 0 or a point. And as a result, this 2 form, which must descend, must be 0 on L. And so therefore you get a flat line bundle on the Lagrangian. And this is very familiar to those who study the Fukaya category, because we know that objects in the Fukaya category are typically Lagrangian submanifolds together with flat line bundles on them. So this is where you get this condition. Okay, on the other hand, the other good example is in the other extreme, where the coisotropic is the whole space. This is called space-filling brane. It's a kind of terrifying thought that your head is expanding to the size of the universe, you know. But in any case, we have this case of the space-filling brane. And in that case, what happens? It's that omega inverse with the curvature, there is no reduction to a submanifold. The reduction is the whole space. And so therefore, F, the curvature of the line bundle, must be non-degenerate. And this combination defines a complex structure on the manifold. And then this combination of F plus I omega must be a complex symplectic form on this complex manifold. So what happens is that your symplectic manifold actually becomes the imaginary part of a holomorphic symplectic structure on the same manifold. So that means that in order to have a space-filling brane, your manifold has to be 4K dimensional to start with. And it has to admit a complex structure and a complex symplectic structure.
And Marco, can I
Yes.
ask a question? Just wondering, this all comes just from being fixed under J? Because before you said...
Yes. Does it seem unbelievable? Does it seem remarkable?
I would have thought that in the case C equals M, it's automatically fixed under J.
No. Because you have this condition X. This is a non-trivial condition. Sorry, what am I saying? Yes, it's true. Yeah, work it out. Yes. Yeah, because this is T plus T star. Then this C, there is no restriction to C, so it's just C is equal to Ix of F. So this means that tau C becomes the graph of the 2 form F in the space-filling case. And that means that we need the graph of F to be fixed by this operation. And that places a non-trivial condition on F.
Okay, yeah, but this is then, of course, dependent on F, not just on the J.
Yes, J is just omega. J is just the symplectic form. F is the unitary connection. The compatibility between them is this. Yeah, that's right. Okay, thanks for asking. You scared me for a second there. Okay, so we have, okay, and so therefore we can find many examples of space-filling branes. For example, if we have a hyperkähler manifold, then we have 3 Kähler forms, omega I, omega j, and omega k. And because of the quaternion relations, we can take the inverse of omega j and combine it with omega k, and that will produce the complex structure I. So we see that if we use omega j as our unitary curvature and omega k as our symplectic form, then it will satisfy the condition required. And so that means that I need omega j to be pre-quantized to a unitary line bundle with connection, sorry. and so whose curvature is omega j. So as long as our hyperkähler manifold has this property that we can pre-quantize omega j, then we get a space-filling brane for the omega k symplectic structure. Okay, but it's not necessary to have the hyperkähler metric. We can just, for example, if you forget about the other if you forget about the metric and you only remember omega j and omega k and I, that's enough information to get your space-filling brane. There's no need to know the hyperkähler metric explicitly, because you can't, from this information, you cannot build the metric. You would need omega I in order to know the metric. Anyway, another example, which we're going to see again before. This one's an important example, but a very simple one. Okay, suppose that we take a complex manifold to start with, and then we take its real cotangent bundle. The real cotangent bundle is, of course, symplectic. It has a canonical symplectic structure. And then we take the trivial line bundle, but for our unitary connection, what I'm going to do is take the canonical one form, and I'm going to twist it or multiply it by the complex structure on the cotangent bundle. Okay, and I'll use that one form to define a unitary connection on the trivial bundle. Okay, so what would be the curvature of this line bundle? The curvature would be the derivative of this one form, which turns out to be the canonical symplectic form twisted by the complex structure. Okay, and so as a result of that, now we have a kind of different real two form, but if we apply omega, the canonical symplectic form inverse to it, we get the complex structure on the cotangent bundle. So in other words, all I'm saying is that if your manifold is a complex manifold, then its cotangent bundle will be a holomorphic symplectic manifold. And so we have a holomorphic symplectic structure where the imaginary part is the real canonical symplectic form on the cotangent bundle, which we all know. It's the phase space structure on T star n. The point is that when n is complex, it becomes completed to a holomorphic symplectic structure. So we have a plentiful source of examples coming from complex manifolds and taking their cotangent bundles. All of those have space-filling branes. Okay, and the final example that I'm going to give is related to this one. And now what I'm going to do is assume that not only is n a complex manifold, but it's also a Kähler manifold. So what happens if we put a Kähler structure? If we put, so I'm just repeating what I said before. If n is just complex, then the cotangent bundle has a space-filling brane just by using the complex structure. But now if we also have a Kähler form, and if this Kähler structure is pre-quantized, so we have this line bundle on n, then we can do the following. We can pull this bundle back to the cotangent bundle, and we can tensor it by the pre-existing one, the trivial one that I started with, and just add the connections together. And then what we've done is twist the space-filling brane into another space-filling brane. So this space-filling brane, it has a different holomorphic symplectic structure. So it has the same imaginary part, just the canonical symplectic structure on the cotangent bundle. But the real part now is the canonical one plus the Kähler form. So this is familiar. This is very familiar to people who know about the magnetic deformation of the cotangent bundle. You know, you can always take the canonical cotangent structure, and then you can pull back a closed two form, and then add that to the symplectic form, and that will always be a symplectic structure on the cotangent bundle. So this is also true in the holomorphic category, but in a funny way. You can take the holomorphic symplectic structure on the tangent bundle of on the cotangent bundle of a complex manifold, and you can pull back any closed 1-1 form and add it to the holomorphic symplectic form, and the result is still a holomorphic symplectic form. But the funny thing is that you're changing the complex structure when you do this. The complex structure has an extra term which involves the canonical symplectic form and the Kähler form. So you get a deformation of the endomorphism on the cotangent bundle, and it shifts the structure of the cotangent bundle. So it becomes a deformed cotangent bundle, and this is called the twisted cotangent bundle by people in algebraic geometry. So you can twist the holomorphic cotangent bundle by any Kähler form, just by pulling it back from the base and adding it on. And that produces you a different space-filling brane. Okay, so now we have two space-filling branes on the cotangent bundle of the manifold N, right? And what I want to point out is that the cotangent bundle of N is a symplectic groupoid for the zero Poisson structure on N. So that means that the cotangent bundle on N has a multiplication, which is nothing but the addition on each fiber. And this multiplication is defined by a Lagrangian relation between M cross M, inside M cross M cross M. And what this allows you to do is to take branes in M, two branes in M, okay, take their product, and then transport it through Lagrangian correspondence to get another brane on M. So in other words, it allows you to multiply branes. Of course, this only works assuming transversality and so on, but in this case, it will automatically hold. So what this means is that I can take this brane, the initial canonical one, and I can tensor it with itself. It turns out that Z0 tensors with itself to give itself back. So it's an idempotent. This canonical one is an idempotent. But if you take Z1 and you tensor it by itself, what you get is a different brane, Z2, which basically corresponds to doubling the Kähler form. So you get a system of branes, Zi, for every integer, and that is a brane constructed from the Kähler form multiplied by I. I mean, multiplied by K, multiplied by an integer. So we get a system indexed by the integers, and it forms a multiplicative system. So that Zi tensor product with Zj gives Zi plus J. Okay, so I just constructed a Z family of space-filling branes on the cotangent bundle of any Kähler manifold.
Marco, how do you get the negative integers?
Well, you can invert. You could just take the minus of the Kähler form and just change these pluses to minuses here and here.
All right, thank you.
But actually, I don't need the minus ones, it turns out, because anyway, but it's a good question. Okay, so I'm finished with a discussion of these branes. So there's plenty of examples. They're mysterious because they're not Lagrangian, and it's the existence of these branes is very threatening. It's very threatening because there's this very famous dictum, which it's my only religion. It's the dictum of Weinstein, of Allen, who said that everything is a Lagrangian. So I don't have it framed on my wall, but maybe I should. Maybe we should all have it framed on our wall. Maybe it should be the global Poisson motto. But the problem is that not everything apparently is a Lagrangian. Some things are coisotropic A-branes. So I don't know if maybe the motto needs to be modified. I'm not sure. So the question now is why? Why do we care about these branes? What's the point about them? Okay, so here I'm going to speak as if I know physics. So I'm going to pretend to be a physicist. My collaborator Maxime Zabzin always makes fun of me because he says that I still have the desire to be a physicist. Well, okay. So let me just explain why branes are important. The reason is that they provide boundary conditions for TQFTs, or for quantum field theories in general. So in a TQFT, you study mapping of, let's say for a two-dimensional TQFT, or a two-dimensional sigma model, we study maps from a two-dimensional surface into the symplectic manifold. And every one of these maps is assigned a certain weight, or what's called an amplitude. And this amplitude is a complex number. In this case, it'll be just a real number. And it's just the exponential of minus the symplectic area of the embedded curve, or the pullback of the symplectic form to the surface you integrate. Of course, you need this to be orientable, or you need to actually it to be oriented in order to define this weight. So every single map has a certain weight, and this weight is provided to you by the symplectic form. And so you're supposed to average over all possible maps, and you're supposed to weight each map by this weighting factor. And you're supposed to compute what's called the Feynman path integral. This is all well and good, but what about when your surface has boundary? You still want to assign a weight to this. And it turns out that if you only assign the same weight as you assigned before, you will have, you will not be getting the correct structure of what's called extended TQFTs. In order to get the correct axiomatic system working for space-times with boundary, you need a boundary term to the action, or you need to change the weight by something on the boundary. And it turns out that the boundary, the way that you do this is that you require that the boundary is mapped to one of these Branes submanifolds. And on that submanifold, remember that we had a unitary connection, and then you can take the holonomy of that unitary connection along the boundary of the map. So basically what you're doing is you're pulling back this line bundle to the boundary, and you're taking its holonomy. Okay, and that's how this weighting factor is modified. And notice that this holonomy will be an element of U1. So you see that this real weight gets modified by a complex number that rotates the weight. And so now when you sum over all possible maps, you're going to be summing complex numbers. These are called amplitudes, and then you're supposed to take the norm squared of the result, and that's supposed to give you the probability. Yes?
Is there a relation between this construction and differential characters?
Yes, of course. In order to see, you can see the combined structure as a differential character, absolutely. Okay. And in general, when you include a brane, so if the codomain here, if the codomain were a generalized complex structure with a background U1 gerb, then it would become even more necessary to use differential characters to define the integral, to define the gerb holonomy and so on. Okay, so what I've drawn here is a picture of the surface with boundary, and you see that the boundary is lying on one of these coisotropic A-branes, which is equipped with a unitary connection that I don't know how to draw. And this is supposed to be just a local piece of the map, of the image of the map. Okay, so what is the TQFT supposed to actually give you if you actually quote unquote quantize it? It's supposed to give you something that satisfies the Atiyah axioms. So meaning that for every cobordism from a one manifold to one manifold, well, the one manifold should be associated to a vector space, and so we have two vector spaces at the two boundary components, and then this surface must give us a linear map between the vector spaces. And if you have the disjoint union of two circles, then we'll get the tensor product of these vector spaces. So in the end, because we have a circle, because the circle exists, we have a certain vector space associated to the circle. And because this pair of pants exists, that means that we have a natural, the TQFT gives us a natural linear map from V tensor V to V. And therefore, and you can check that by drawing, by sewing the pants together in pairs in different ways, you can check that this is an associative multiplication. And so as a result, the TQFT assigns to a circle what's called a commutative Frobenius algebra. And in the case of a symplectic manifold, this commutative Frobenius algebra that the TQFT produces when you evaluate it on the circle is called the quantum cohomology of the symplectic manifold. It's a famous commutative algebra associated to a symplectic manifold. All right, but notice that here there are no boundaries on the basic objects that we are considering. So in other words, the one manifolds that we're considering do not have boundary. So now let's allow them to have boundary. So now we have an interval with two boundary points, which lie on these two boundary conditions, on these two coisotropics, C1 and C2. Well, the same should hold, that associated to this interval with boundary, with labeled boundary, I should have a vector space. And similarly here, for this interval with labeled boundary, I should have another vector space. And this surface, this cobordism of intervals with boundary, should be associated to a linear map. This is called extended TFT. when you go from the no boundary to the boundary case, it's called, well, the first step is, it's the first step of extended TFT. And now what happens is that, now look what happens. So now the analog of the pair of pants is this diagram. We have two intervals with labeled boundary, and they go to one interval with labeled boundary. So this means that I'm going to have three vector spaces in the mix. I'm going to have V C1 C2, the vector space associated to this, the vector space associated to this, and the vector space associated to this, and I will have a multiplication from this tensor product to this tensor product. But now these vector spaces are no longer the same, because it's not a circle, circle, circle. These are different labelings. And so that means that I'm going to have, for every pair of labelings, I will have a vector space. And then for every triple of labelings, C1, C2, C3, I will have a composition map. And what that means is that we get the structure of a category just for free. So in other words, we define a category where the objects are the labels and where the morphisms are the vector spaces that this TFT assigns to the interval with labeled boundary by C1 and C2. We define HOM C1, C2 in this way. So in this way, the boundary conditions, which consist of coisotropic A-branes, they form a category, and this category is known as the Fukaya category. Okay, so this is how we obtain a category from these boundary conditions on this model. Now, there's an asterisk here because of the fact that in actual fact, if you look at any book where the Fukaya category is defined, the objects are not allowed to be any coisotropic A-brane. They're only allowed to be Lagrangian. So this is, you could say that it's historical accident or convenience or ignorance or whatever, whichever you would like to use as an excuse for this, but it is bizarre that the Fukaya category is defined only using some of the objects in the category, or some of the boundary conditions. Nevertheless, that's how it is.
Marco, why is it not the symplectic cohomology? Why the quantum cohomology?
I guess it could be the symplectic cohomology, but in the usual case for a projective variety, the vector space is the quantum.
In the compact case, it'll be the same, I guess. But for non-compact, I was told that.
In the compact case, this is the quantum cohomology. But I guess in the case of a Weinstein manifold, then it would be the symplectic cohomology. Yeah, thank you.
But Marco,
yes.
I thought it wasn't bizarre because these new branes have resolution.
Yes, Ezra. I'm getting to that.
Well, all right, but okay, so your rhetoric's a bit overheated.
Well, I don't know. I mean, at the time that the Fukaya category was defined, these branes were not known.
Right, but as soon as I spoke to Kapustin as he invented these new branes, and he informed me that they did have resolutions by Lagrangians. Well,
so I'm getting to that, and that is the case. That is the case for some symplectic manifolds, yes, but not
correct.
all.
Yeah, exactly.
So therefore, my rhetoric
the ones
is
that
correct.
Fukaya had considered, let's say.
Well, nevertheless, what I said in my so-called rhetoric is true, that there may be objects that are not captured in the completion of the Fukaya category.
This is correct, yes.
Yeah, thank you. Okay, so let's get to that. So that's exactly the first thing I want to discuss. I'm just checking my time, and I'm realizing I have 25 minutes. Okay, that's fine. So Kapustin and Orlov, they discovered coisotropic branes by investigating the symplectic manifold, which is the 4 torus. And they investigated this example because mirror symmetry is very well known for tori. And so they could compare the Fukaya category of T4 with what it's supposed to be isomorphic to on the mirror side. On the mirror side, we have the product of an elliptic curve with itself or some other abelian variety of dimension 2, of complex dimension 2. And so mirror symmetry states very clearly and that the two categories, the Fukaya category on one side and the complex derived category of coherent sheaves, should be isomorphic. But what they found was that there were additional objects on the in the complex geometry side which were not representable by Lagrangians. So they knew that there should be something besides Lagrangians in order for mirror symmetry to be correct. So so what they used is this basic fact that a symplectic T2 is mirror to a complex elliptic curve. And the objects on the left side are Lagrangians, which I've drawn as a red circle embedded inside the T2 with a certain slope. And this Lagrangian with a certain slope becomes a holomorphic vector bundle on the mirror side, a holomorphic vector bundle on the elliptic curve of a certain degree and a certain rank, which depends on this slope. And there is a freedom here of translating the Lagrangian to the left or to the right. This gives us an S1 degree of freedom, and this S1 degree of freedom, it corresponds to translation on this side. But the problem is that the translation on this side involves a translation in two directions, and so this translation has 2 degrees of freedom. The elliptic curve acts on itself by translation. And so that means that we have a problem that here we only have 1 direction of translation, and here we have 2. So this is repaired by considering the holonomy of the line bundle on this circle, right? The object is not just a Lagrangian, but it's a Lagrangian with a unitary line bundle. This unitary line bundle has a holonomy, and this holonomy is in U1. So together, the translations and the holonomy gives us a torus of degrees of freedom, which is mirror to the translation action of the elliptic curve. So everything that you would like to know about the symplectic geometry of this curve, of this 2 torus, would be captured by the complex geometry of this curve. That's what they used for the case of T4. So Kapustin and Orlov, their argument was like this. This is how their argument went. So if we use a very special curve E, which is this curve, where it's a curve with complex multiplication, so that we're using the square lattice. Okay, so if we use the elliptic curve with a square lattice, then it has an automorphism which is multiplication by I, which is a rotation of the entire elliptic curve. This is an automorphism of the curve and therefore an automorphism of the category. And we can represent that by taking the graph of the multiplication, and that would be a complex submanifold of E cross E. And this is a complex submanifold, and therefore it's a brane. It's an object in the derived category. And so this abelian variety is mirror to this T4, and this graph of the multiplication should correspond to something. But what they noticed is that this object cannot be Lagrangian. It must be of higher dimension than a Lagrangian submanifold, and they concluded that it must be one of these coisotropic A-branes. Okay, so we took, together with my student Josh Lackman, we've been taking a closer look at these coisotropic A-branes. In this case, on T4, if we use coordinates x1, y1 as Darboux coordinates on T2 and x2, y2 as Darboux coordinates on the other T2, then you can find a unitary line bundle with this curvature. And then this curvature combines with the symplectic form to produce a holomorphic symplectic form on T4, which mixes, you see, like the holomorphic coordinate in this complex structure, it mixes one of the Darboux coordinates on this T2 with another Darboux coordinate on this T2. Those 2 Darboux coordinates match up together to produce a complex coordinate, and we get a holomorphic symplectic structure in this way. And so the question is, can we understand in a geometric way what this object corresponds to in the symplectic T4? And so what we proposed is the following type of transform. So we said that suppose that we view T4 as the product of T2 with T2, with the two symplectic projection maps. We can take a Lagrangian in here, in this T2, and then we can, this is just a Lagrangian circle. We can pull it back. This will now give us a T3 sitting inside the T4. Then I can tensor this pullback by the space-filling brane. This would give me another unitary line bundle on the T3 inside T4. Then the projection to T2 has circle fibers. And so we can try to push forward along the circle fibers. But the problem is that this connection after push forward, it will not be flat along that T3. So we cannot necessarily take global sections along the fibers. It's the usual problem of Bohr-Sommerfeld orbits. So we need to look at those fibers where there is actually a global section. And it turns out that those will be the fibers above a collection of points in this T2, and that collection of points assembles to produce a Lagrangian submanifold. And then when we take the global sections, that will give us a line bundle on this Lagrangian submanifold, and that line bundle will be will have a unitary connection. So what this means is that given a circle with a unitary connection, we can pull it back, push it forward by using the Bohr-Sommerfeld leaves, and we'll get another Lagrangian with a unitary connection. And in this way, we get a functor from the Fukaya category of T2 to the Fukaya category of T2. So this defines an endofunctor of the Fukaya category of T2. And this endofunctor is not in the image of the well-known map, which has been studied by Abu Zaid and Smith, which goes from objects of the Fukaya category of T4 and converts them into endofunctors of the Fukaya category of T2. This is a fully faithful functor, but it is not it is not surjective. So this functor that we defined in this way is not in the image of this functor. On the other hand, there is a way of completing this Fukaya category. So this Fukaya category has a certain defect. The defect, you could think of it as a defect in the following sense, that it doesn't have the ability to take direct sums. We haven't defined what it means to take direct sums of Lagrangians, and we haven't defined what it means to shift them in degree. Okay, so if we wanted to repair those defects, what we do is consider these things called twisted complexes, which is essentially a completion of the category, which includes sums and shifts. And then this category of twisted complexes, it has yet another defect. This defect is that it may occur that you have an object in the category with an idempotent endomorphism of the object, meaning that we have an object and we have an endomorphism which squares to itself. The fact that it squares to itself means that it looks like a projection operation on the object itself, almost as if it was a projection to a sub-object. And the problem is that we don't have kernels and images. This is not an abelian category. So we cannot produce the image of the projection. We cannot somehow separate out the sub-object from inside the object. So the solution to this is that we do the idempotent completion, otherwise known as the Karoubi envelope. It was invented by Karoubi in his study of, and the result after doing this idempotent completion is that we obtain a larger category, and in this larger category we carefully checked that this functor defines an object, and this object is indeed mirror to the graph of multiplication by I in the derived category. So in other words, the point of this is to kind of understand how these coisotropic branes geometrically determine objects of the completion of the category, so that eventually we could potentially study the problem of whether doing this idempotent completion of the twisted complexes, whether that always captures all coisotropic objects. I would guess, I mean, we have no reason to believe that coisotropic A-branes are always captured by this completion operation, but at least in the case of T4, it seems to be the case. In fact, it is, well, yeah, it seems to be the case. Okay, let me just check time. How much time do I have? 15 minutes, right?
Could I ask a question or a
yes?
Yeah, you can go on. Yeah.
Another aggressive intervention.
Yeah, go ahead. Yeah.
Yeah, so actually the idempotent completion is not the idempotent completion of Karoubi. It's a generalization for differential graded or A infinity categories.
Yes, okay, I apologize. You're absolutely right. Yes, thank you.
Oh, okay. I just wanted to double check. Okay, yeah. No, because you know, there are a lot more terms then in the data. And so you have a lot more flexibility to produce. You know, it's a lot less rigid.
It's all right. That's besides the point of my talk, but thank you for the correction.
Oh.
Okay. So
well, Marco, you have a little bit more of time because you started 5 minutes late. So
oh, okay. All right.
You can talk until 20.
In that case, I definitely will finish on time. There's no question. Okay. So now that we have seen you know, what branes are and how they play a role in the category associated to a symplectic manifold, you know, they basically give us objects in the Fukaya category which could be considered as exotic in the sense that they may or may not be in the completion of the subcategory generated by Lagrangians. So that you know, brings up many questions of its own, and so we really need a lot more kind of fundamental work on the study of these branes in symplectic manifolds, just as such. Okay, but instead of pressing on with that, let me kind of try to use these branes for a different application. Hoping that we can one day, you know, embed them into a larger category, which should be called the complete or the full Fukaya category. So what can we do with these things? Well, it turns out that they can be very profitably combined with the idea of symplectic groupoids. So I'm going to give one example, which you can find in a paper of Gukov-Witten about quantization from 2007. Okay, so let's look at S2 and take its cotangent bundle with a canonical symplectic form. This is our symplectic manifold. We will be concerned with the Fukaya category of this. Okay. Now, we know that S2 is secretly a complex manifold. It's CP1. And so we know that this cotangent bundle does have a holomorphic symplectic structure. And so what that indicates is that this thing will have a space-filling brane. And it has dimension 4, so it's the right dimension to have a space-filling brane. So let's see how that looks. So suppose that we choose a Kähler structure on the S2, and we pre-quantize it to a line bundle, which is normally called O1 with the Fubini-Studi symplectic form. Okay, then this gives us, by the construction that I outlined before, a space-filling brane. What does it look like? Well, it's supported on the whole manifold, T star S2. It has a line bundle. The Hermitian line bundle is just the pullback of the pre-quantum line bundle. And the Hermitian connection will be the pullback of this Chern connection plus this correction term coming from the complex structure applied to the canonical one form on the cotangent bundle. So I'm shifting, oops, I didn't mean to do that. I'm shifting the Chern connection after pulling it back. So in the end, what I get is a space-filling brane with this holomorphic symplectic structure. Notice that it looks like the canonical plus I times the canonical. So this part, the first and third terms, these are the holomorphic symplectic structure on the holomorphic cotangent bundle, but I'm shifting it by a magnetic term, which is the pullback of the Fubini-Studi. So this symplectic form, this holomorphic symplectic form, is not the holomorphic cotangent bundle, but rather what's called the twisted holomorphic cotangent bundle. This is an affine holomorphic symplectic variety. It's just an affine quadric. Okay, and so as a result of this construction, we have not one, but two branes inside the cotangent bundle of S2. We have the space-filling brane that I just built, and we have the Lagrangian zero section, which no one would object to. So as a result, what happens when you have two objects of a category? Well, you have a Hom space. You have a Hom space from this object to this object, and then you have a Hom algebra from this object to itself, and you have another Hom algebra from this object to itself. And these two algebras will act on this as a bimodule. Okay, so if we had the category structure in hand, we could produce three vector spaces, these two being algebras, and this one being a bimodule for the action of both. And in this case, Kapustin and Gukov and Witten, they kind of computed this in the sense that they essentially knew the answer and just wrote it down. And I have no doubt that their answer is correct, although the problem is that we don't have a definition of this extended Fukaya category, but nevertheless, their answer is the following, that we basically have just the field here, and for experts, I'm only looking at the degree zero part, which is what they do in their paper. Anyway, so you have the field, so it's a commutative algebra, the Hom from the Lagrangian to itself. And then here we have the geometric quantization of the S2. And this is the essential idea of their paper, because they're trying to explain that geometric quantization is actually a Hom space between a Lagrangian and a space-filling brane. They believe, or they propose in this paper, that it's always the case. But not only that, we also get this. So on the algebra on this side is a non-commutative algebra, which is obtained by taking the universal enveloping algebra of SL2C, which is acting on the P1. This is like holomorphic vector fields. And we mod out by setting the quadratic Casimir equal to 1/4. This is like spin 1/2, because this is a two-dimensional vector space. This is the part of the universal enveloping algebra which acts on spin 1/2 representations. And so you get this this algebra, this non-commutative algebra acting here. So so they're providing us with the results.
Marco, there is a question.
Oh yeah. So they're providing us.
Anton?
Yeah, sorry, this spin 1/2.
Yeah.
Does it depend on the Hermitian line bundle that you?
Yes, it's exactly because you see that the structure of this space-filling brane includes the pre-quantized Kähler structure. So if I double this symplectic form, then I'm going to get a different structure on this twisted holomorphic cotangent bundle, and this will be a different brane, which we should then call Z2. And then the Hom from Z2 to itself would change the value of the quadratic Casimir.
Mm-hmm. Okay.
It would give a different algebra.
Sounds good.
Okay. Now, okay, so the question is that no one has really provided a method for how to compute the Homs between a Lagrangian and a space-filling brane. There have been special cases computed by Aldi and Zaslow, by Kapustin and Witten, and by Gukov and Witten, but there is no general procedure. So, and I'm not going to provide a general procedure, but I have the following proposal. So this is how we'll do it. The first thing will be, there's 4 steps. The first step is that we should choose a holomorphic Lagrangian polarization for the space-filling brane, and we should choose it to be transverse to the Lagrangian brane. So this now is making use of the holomorphic symplectic structure that the brane has on it, which is, remember, it's kind of coming out of nowhere. It's not part of the underlying symplectic geometry. Nevertheless, we'll use it to try to define this polarization. Then what we should do is lift this line bundle on Z to a holomorphic prequantization. So I want a holomorphic connection whose curvature is this holomorphic symplectic structure. So now we're really making use of the holomorphic symplectic structure. And then take holomorphic flat sections along the Bohr-Sommerfeld leaves. And this will give what? Well, if you have this fibration by Lagrangian holomorphic Lagrangians and you take holomorphic flat sections, then on the parameter space for the Lagrangians, you will get a holomorphic sheaf. And then this holomorphic sheaf, which could be like it could be, it doesn't have to be a locally free sheaf. It could be just some other sheaf. This is called family Floer theory. It's a holomorphic family. It's a holomorphically varying computation in the Floer theory. And this sheaf, we could then take global holomorphic sections of, or take a higher derived functors of the global section functor. So this is
I didn't understand what you mean by the polarization parameter space.
Well, for this purpose, I'm going to assume that the polarization is a Lagrangian fibration of some kind over a complex manifold.
Oh, the leaf space of the
leaf space.
foliation.
Yeah, the leaf space.
Oh,
so the point is that we want to convert the space filling brane into a sheaf on the leaf space.
I see. But that's still a complex, let's say, manifold or maybe space.
Yes, it's a holomorphic space of some kind. Yeah.
Yeah. So my question is when you say sheaf, is this expected to be a coherent sheaf?
Yes. Yes.
Or quasi-coherent or something?
Yes, a coherent sheaf, because it's obtained from taking pushing forward a holomorphic sheaf.
Oh, fine. Good. Okay. Yeah. Perfect. Okay.
Okay, so what if we do this in this particular case? So this is a really simple case, but let's take the case of Gukov-Witten and see what this would give. I have my twisted cotangent bundle, I have my Lagrangian, and I have my space-filling brane. Well, the twisted cotangent bundle turns out to have plenty of different polarizations. But let me choose one, which is the polarization by the affine fibers. This is an affine line bundle over P1 in the holomorphic category. It's not a holomorphic vector bundle, but it's a holomorphic affine bundle. And of course, the fibers are holomorphic Lagrangians. So if I push this thing forward, I will get a holomorphic sheaf on P1. And that holomorphic sheaf is indeed O1. And if I take sections of it, I get what I'm supposed to get, which is what they wanted. It turns out that there's another possible polarization here, which is to use the toric structure of P1. The toric structure gives a moment map which is defined on P1. But that moment map lifts to a holomorphic moment map on the affine cotangent bundle, on the twisted cotangent bundle. And that holomorphic moment map gives us a Lagrangian foliation, a Lagrangian fibration of this space-filling brane. And that one has discrete Bohr-Sommerfeld leaves. And it turns out that if we take the push forward of that and compute its global sections, we get exactly the toric decomposition of this vector space into the what do they call them? The isotypic components, the Z cross Z, the Z graded components, or the Z to the N graded components. So we seem to get the right answer with these two different choices of holomorphic Lagrangian polarizations. Okay, so and then we could now, so we only obtained in this way one particular Hom space between L and Z1. But remember that we can use the groupoid structure of T star to convolve Z1 with itself to get Z2, Z3, Z4, a bunch of space-filling branes with higher and higher Chern class. So if we do that, then we'll get a sequence of space-filling branes. But the zero section is idempotent. So what that means is that we can take Homs between L and Zi and Hom between L and Zj, and that will have a natural map to the Hom from L tensor L, which is just L because it's idempotent, to Zi tensor Zj, which is Zi plus J because it's a multiplicative system. So as a result of the fact that these space-filling branes form a multiplicative system, we get an algebra structure on these Hom spaces between two branes. Okay, and this gives us an algebra structure on this sum of holomorphic sections, which turns it into a Z-graded algebra, which is the homogeneous coordinate ring of P1, as you would have expected. Okay, but this picture has now, so what we've done now, I'm kind of ending now. So what we've done is to express this Z-graded algebra in a way that that makes use of the groupoid structure of T star S2. Okay, but now with Francis Bischoff, what I've been doing for the past year or so is that we want to extend this to non-trivial symplectic groupoids. So our first family of examples is the following. If you take a toric scalar, which is pre-quantized, and if you take a complex R matrix and you push it forward to the toric variety, what you'll get is an invariant holomorphic Poisson structure on the toric variety. And then what we'll do is we'll take the symplectic groupoid of this Poisson structure, actually of its imaginary part. Whether you take the imaginary part or the holomorphic Poisson structure doesn't really matter. This has been extensively studied by Ping Xu and his collaborators. So what Ping did quite a long time ago is he explicitly constructed the symplectic groupoid for such a R matrix Poisson structure. So, and he showed that this total space of the groupoid is really just the cotangent bundle of M. So it's unusual for a symplectic groupoid to be just the cotangent bundle. This is called exponential type by Alan Weinstein. But in this case, it happens to be so, exponential type. So as a result of this, we can actually copy the same construction. We can produce a space-filling brane by taking the canonical holomorphic symplectic groupoid structure and adding the magnetic deformation, which in this case becomes adding the source pullback of the Kähler form. And it turns out that this is our space-filling brane with Chern class 1, if you wish. Okay, and then we can convolve this thing with itself and produce a Z family of space-filling branes on the symplectic groupoid of the toric variety. And we can also get this convolution algebra structure in the same way, and very explicitly. But in this case now, the composition comes from the structure of the groupoid, and it involves the convolution structure of the groupoid. So we get a non-commutative version of the toric variety. Interestingly, each one of these summands is still a Hom from a Lagrangian to a space-filling brane, and so it still has the action of Hom ZK ZK on it. And this Hom ZK ZK is the same algebra as that which was constructed by Gukov and Witten. So that means that this thing, despite the fact that the algebra is now non-commutative, each summand in the algebra still has an action by SL2C. So it's kind of funny that the non-commutative variety still has the SL2C action. Okay, so to conclude, oops, what did I do? How did I manage to do this? Ah, okay, good. So just to conclude, I just wanted to indicate some future steps that we hope to explore in the coming years. Any generalized complex manifold, okay, through the work of Kreinik, we know that it has a partial integration to a real symplectic groupoid. Okay, so there's a real symplectic groupoid sitting over any GC manifold. And if we take the source and target together and produce what's called the anchor map from the groupoid to M cross M, it turns out that this map is a generalized holomorphic map. It relates the symplectic structure on the left to the generalized complex structure on the right. And if we are given a pair of branes, C1 and C2, in this GC manifold, then we can take the pre-image of the brane under this generalized holomorphic map, and it automatically will be a brane inside G. And that means that it will be a coisotropic A-brane. So this is actually a mechanism for producing more examples of coisotropic A-branes. It turns out that any pair of branes in a GC manifold can be converted into a coisotropic A-brane. And so if we are able to extend the Fukaya category of the symplectic groupoid to include these coisotropic A-branes, we could define the Hom from the identity section of the groupoid to this A-brane, and we would obtain a vector space which would serve as the Hom space between these two branes. And it would give at least some kind of definition of a category of generalized complex branes. Okay, I'll leave it there. Thank you for your attention.
think we have a lot of questions, additional questions. So you can raise your hand. Alejandro has a question. You want to talk?
Yes, thank you. I have actually two questions, but I will focus on the.
You can make two questions if you want.
I can? Okay, thank you. Very generous. So, do you know any example, like in the second half of your talk, generalizing the Groupoid-Witten idea of quantization, where the groupoid looks more like a pair groupoid instead of a cotangent bundle?
Well, you know, the first example that I gave was a space-filling brane on T4, and I was really using the fact that it was T2 cross T2. And in fact, the symplectic structure on it was T2 minus cross T2. So that example is of the type you're talking about.
Right. And can you get a non-commutative algebra out of the pair groupoid multiplication?
Well, okay. So it's funny that you should ask that. The reason is that the T4 example is is actually, there's a step in the quantization proposal which is obstructed in that case. Because remember that I had to have a holomorphic pre-quantization of the holomorphic symplectic structure. So it turns out that on T4, if you look at the holomorphic symplectic structure, that does not have a pre-quantization. It only pre-quantizes to a gerb connection. And so the point is that it seems like a genuine algebra is not possible in that case, which actually makes sense because in the non-commutative algebra literature, we know that for T4 and for the K3 surface, there is no graded algebra corresponding to them. So yeah, it's kind of tricky. Like, I think that in that case, there is no non-commutative graded algebra and there shouldn't be.
Okay.
But yeah, I mean, you could ask, do you know an example that looks like a pair groupoid, but where it does work? And the answer is no for now. Yeah, I can't think of one.
Okay, thank you. I will keep the question for later.
Okay.
Okay. More questions? I have a question myself. In the examples that you are giving, you are always taking like a pair groupoid or cotangent bundle of a two-dimensional. You have higher dimensional examples.
Well, actually, so what we said, it works for toric varieties in any dimension.
Yeah, it's true. Okay.
But you're right that it's a cotangent bundle. So
yeah.
So what we're Francis and I and Francis, Josh and I are working out. We're trying to work on this example of the smooth elliptic curve inside CP2 and other degenerations of the smooth elliptic curve in CP2. Okay. So we're hoping that at least in some of those cases, we're able to make the thing work. But so far, so far we're still writing up this one.
So if I understood this,
the main problem is to move away from toric. Yeah.
Okay, because there you have all the examples of the polarizations, I imagine.
Yeah, exactly.
You have a sort of independence of polarization in your construction.
Well, yeah, the fact that it's independent of polarization, I have no idea why. It's mysterious, yeah. Presumably, it has something to do with the Floer theory on these non-compact holomorphic symplectic manifolds, but I don't know. I don't think it's known why such a thing might be true.
Yeah, that's very interesting. Yeah, thank you. Thank you. Do we have more questions? Otherwise, Alejandro, you can make a
question.
Leonid, I think, already has a.
Okay. Sorry, I didn't see this.
Hi.
Leonid, go ahead.
Yeah. So.
Hi, Leonid.
Hi. So in usual Foucault category in Lagrangian situation, so you define this home via Floer homology, right, which takes into account Lagrangian intersections and then solves some elliptic problem, and computes some moduli spaces and so on. So
yes,
is there any analog of this in the situation which you propose.
Yeah, so this is so yeah, so the problem with that is that in the physics literature, they don't provide what this elliptic problem is. They don't know. They appear not to know how to set this thing up properly. Okay. Now, on the other hand, in the few computations that they do provide in the physics literature, they give some arguments why we have finite dimensional answers, for example. Okay, and if you ask them, you know, why is it that you're getting a finite dimensional answer, they would say that there is a that the supersymmetry is giving you is giving you a kind of BRST complex, and that a certain cohomology group should be finite dimensional. Okay, now on the other hand, if you look closely at this paper of Aldi and Zaslow, where they actually compute these Hom spaces very carefully from a physics point of view, okay, what you notice is that at a part of the calculation, they make a crucial assumption, which is that they assume that the space-filling brane is polarized. And actually, the polarization that they pick happens to be a holomorphic Lagrangian polarization, even though they don't notice that. Okay, so what it points to is the possibility that maybe it's really necessary to polarize this thing by Lagrangians, and maybe it's really necessary for the Lagrangians to vary holomorphically, and maybe what that results in is a holomorphic family Floer theory. Maybe it's just a Floer theory computation, but in a holomorphic family. That's possible. When I speak to the physicists about this, it seems conceivable, but they don't really seem to have any guidance on this point.
Thank you very much.
Okay, thank you. We have a question by Thomas Hausel.
Yes.
Thomas.
Yes, hi. Thanks for the great talk. So I have two questions. One is probably quick. So you mentioned two space-filling branes on. One was the hyperkähler situation. In a given complex structure, you have, I think, what is called canonical coisotropic brane.
Yes.
And then you had the second construction on the cotangent.
Yeah, which is like it's like moving the value of the hyperkähler moment of the holomorphic moment map. If you just change if you instead of taking the zero value, if you take like a non-zero value, then you would be deforming the holomorphic symplectic structure. That's what it is.
Right, but in the case, the specific example, you had T star S2. There is the Eguchi-Hanson metric.
Yeah, so
example,
the two branes that I was talking about. So Z0 is just the holomorphic cotangent of P1.
Yes.
Which is the I complex structure, let's say. And then Z1 is the is like the other complex structure that you would get by taking the one value of the moment map.
Right.
So it's the one that's just an affine quadric. Right. And then the other ones are just scalings of that one. So it's isomorphic as a variety, but the holomorphic symplectic structure is scaled by a multiple of 2, or by n, by k, let's say. So you have to assemble all of those, and you get a Z family of space-filling branes.
Right. Okay. Yeah. Good. So, and then the other question was what Ezra mentioned. I didn't catch it later in the talk, that you can resolve a coisotropic brane with Lagrangians. How does it work? What's the
right? So the point is really that's what I was doing carefully with Josh Lackman. So the point is that you have to. Can you see the slide that I put up?
Yeah.
So you have to take the standard Lagrangians inside T4. Like you could even take generators. So you could take products of circles of different slopes in the T2s, take products of them and get Lagrangians in T4. And then you should produce a twisted complex of these Lagrangians. So that means that you're going to have a sequence of these Lagrangians with maps between them, right? And then you're going to, so that will be your initial object. But then what you'll do is you'll produce an endomorphism of that object, which squares to itself. And that will be the projector. And the idea is that it will be a projection operator to some subobject, but the subobject doesn't exist as a twisted complex. So you need to formally adjoin it. So the answer is that what you're supposed to do is you're supposed to produce a sequence of Lagrangians with maps between them in the Fukaya category. And you're supposed to produce an endomorphism of that sequence, which squares to itself. And that data determines an object in the completion. And that completion is where these things live.
So what about the canonical coisotropic brane? Does it have a...
That's the one that we computed. Yeah. So
okay.
we computed it as it's like a 3-term complex with this weird endomorphism. Yeah. So it's a complicated object when you write it in terms of Lagrangians.
So this is available, this paper? Or?
Well, we're writing it. We're writing it now. I'm glad that you'll be interested in it because I thought maybe no one would be interested in seeing this bizarre construction.
Thank you.
We have a question by Rui.
Yeah, hi Marco.
Hi Rui.
How are you? Good talk, really nice talk. So something that it's not so clear to me, maybe you explained, but I didn't get it. When you consider these branes on a groupoid, on a symplectic groupoid, your definition doesn't seem to interact at all with the groupoid structure a priori, your definition of brane.
No, it doesn't. No.
But the examples that you consider, they all seem to interact with the symplectic groupoid structure.
Yeah. So think of it like this: that in a groupoid, right? It's possible that you could have a brane that convolves, that squares to itself, right? So the 0 section, if you square it in the convolution algebra structure, if you take L cross L and then you transport it by the multiplication, you get back the 0 section. So the Lagrangian object, you could say, is like what do they call it? It's like an algebra object or something inside the Lagrangian monoidal category, right? It's an object that squares to itself. And so you could say that it's multiplicative in some sense. Okay, but if you pick a random Lagrangian, then you could then it won't square to itself. It'll square to something else, L2. And then if you take the third power, you'll produce a sequence of objects. And that whole sequence, you could say, is a multiplicative sequence. So that's what I'm doing. I'm basically picking something which is not essentially multiplicative, and I'm completing it by taking powers of it to get something that, is closed under multiplication. That's how I get the algebra.
But you could also consider a priori objects that were multiplicative, say coisotropic subgroupoids, together with this data, which you would still have to make it multiplicative in some sense.
Absolutely.
The line bundle and the connection.
Yeah, for sure. And you could, definitely.
Is that interesting at all? Or?
Yeah. I mean, for example, if you picked a coisotropic, then there would be a coisotropic subgroupoid, and there would be a Lagrangian subgroupoid which acts on it, and it would take a quotient, and you would get the symplectic groupoid of the quotient. And so that's what you would consider, that those objects that you just mentioned, you would consider them if you wanted to understand functors from the Fukaya of the initial groupoid to the Fukaya of the quotient groupoid. Those would be very, very useful for that purpose.
Okay, thank you.
No more questions?
I have one more naive question.
Okay.
So what about homes between space-filling branes? Or should one construct them by resolving into Lagrangians, or what's the...
Yeah, so that's exactly the idea that I tried to pursue. So I tried to recover this universal enveloping algebra quotient. I was trying to obtain that by resolving this thing into Bohr-Sommerfeld branes and so on. So that's inconclusive at this point. I hope that it's possible, but so far I have no method for computing that.
Okay, thank you.
It's an important problem. Yeah, we don't know. But certainly, yeah, it's a bit, it kind of indicates that, I mean, actually, so in the paper by Gukov and Witten, they even claim that if the A model of the cotangent bundle, or if the A model of this larger space is truly well defined, then the holomorphic Poisson structure should have a quantization. So, I mean, that's a quite tall order, right? Because we're not talking about deformation quantization. We're talking about real, true quantization. So yeah, I mean, we shouldn't expect this to work in all cases of holomorphic Poisson structures, but at least for the cases that I'm interested in, we should definitely expect it to work. Like for the, for these CP2 examples.
Okay, great. Thanks a lot, Marco, for this wonderful
Okay,
talk.
thanks a lot for everyone attending.
So we are looking forward to reading the long paper. This is going to be a long paper on the archive.
No, it's going to be short. I'll make it as short as possible, yeah.
Okay, thanks a lot for the talk.
Okay. Take care.
And well, let's thank again Marco. Remember that next week we have we are still here. It's August, but we are still here with the Poisson seminar. Next week is Enrique Bursting who will give a talk. Title is still to be announced. Hope we will know about soon. See you soon. Bye.
The title has already been announced.
Oh, sorry. What's the title, Nikita?
The title is Morita equivalence of formal Poisson structures and links with deformation quantization.
Okay, good, great. No questions on YouTube, by the way. We didn't get any questions from Mark on YouTube. Everything was live, but I think you got enough questions.
Anyone on YouTube, it's crystal clear.
Exactly. A lot of hertz, little hertz, and these kind of things. Okay. Okay, thanks, Marco, for your talk.
Yeah, we
See you
have
all.
3 likes. 3 likes.
3 likes. One is me.